I'm going to show you an example. Hope this example will give you some idea how to prove your do your homework for one of the problems. Okay, so the example I'm going to show you is the following: that I have this sequence. Okay, I have a sequence 1, 1/2, and 1/3, and keep going like 1 over n, and keep going like this. So if you look at this sequence, the limit is 0. Okay, limit n going to infinity, 1 over n is equal to 0, right? And we want to show the average also goes to 0. So what it means is that 1 over n sigma k goes from 1 to n, 1 over k, and that's 1 over n, 1 plus 1/2 plus 1 over n. That one goes to 0. Okay, so how do we do this? We will do the following thing. That means we need to do the following thing. Given any epsilon greater than 0, we need to show the following thing. We need to show when n is big enough, 1 over n sigma k from 1 to n, 1 over k, this one over here is less than epsilon. And this is called the epsilon n language, right? So that's what we're going to do. So let me give you an example. This is just an example. In general, we need to use epsilon. For example, over here, let's say epsilon is equal to 1 over 100. Okay, I'm going to find a very specific little n, so that when n is bigger than that, then it's going to be less than epsilon. So we're going to do this. And the idea is, look at this sum over here. We look at 1 over n and 1 plus say we have 1 over 100 and plus 1 over 101, and I keep going until 1 over n. We know 1 over n is average, right? So in order for this one to be small, we just need to look at what terms actually are contributing the most of the sum. So we look at this one over here. If we look at this one over here, we see average over here is smaller than 1 over 101. And that's good, because we want to show that this average is less than 1 over 100. But since we have the front over here, so we're going to do this. We're going to actually look at the sum over here more carefully. The idea is that we look at the sum. This is part 1. This is part 1. And then we have over here part 2. Okay. Here is part 2. And we're going to show part 1 is less than 1 over 200. And then part 2 over here is also less than 1 over 200 when n is large. When n is large. If that's true, then we have the sum is going to be less than 100, right? And if we look at the part 1 over here, look at the part 1. Part 1 we have 1 over n, and we have 1 plus a lot of things over here. But this is a finite sum. This is over here is finite sum, right? And in fact, you can see this is going to be less than or equal to 1 over n and 1 plus 1. We can just estimate, and we have over here 200 of them. So this is equal to 200 over n. And we can definitely make this one to be less than over 200. How do we do that? We just need to make n to be greater than 40,000, right? If n is bigger than 40,000, then 200 over n is going to be less than 200 over 40,000, and that's going to be equal to 1 over 200. So this is for part 1. And for part 2, it's easier because now we have 1 over n, and then we have 1 over 201, and then over here. And if you look at how many terms we have, this is n, this is 201. So we have over here n minus 200. So this is going to be less than or equal to 1 over n and 1 over 201 and 1 over 201, right? Because the first one is the largest one. And from here, then we can see this is going to be equal to n minus 200 over n and 201. And we can easily see this is less than 1 over 200 because this is less than 200 and n minus 200 over n is less than 1. So now we don't even have any requirement on n to be big. As long as n is bigger than or equal to 201, that's going to be good enough. So putting them together, so we have this. For epsilon is equal to 1 over 100, we have the following. We have the following. If n is bigger than 40,000, then 1 over n and 1 plus 1 over 200 and keep going until 1 over n is going to be less than 100. Of course, for any epsilon bigger than 0, we can do this. So when n is sufficiently large, we can show that part 1 is going to be less than epsilon over 2, and also part 2 is going to be less than epsilon over 2. And then what it means is that 1 over n and 1 plus 1 over 2 plus 1 over n is going to be less than epsilon over 2 and plus epsilon over 2, and that's going to be epsilon. And then that's the end of the proof, because for any epsilon bigger than 0, we can find large enough n so that this is true for all n. For all n bigger than or equal to some kind of capital N. Okay, and that's the idea. All right.